Hello, everybody. My name is Jared Brown. I'm a first-year master's student here at the University of Oklahoma, and I am going to be talking about damage zone estimation using rejected noise computed from AASPI's structure-oriented filter. Now, just so we are clear about what I am talking about when I say damage zone is the secondary propagation of fractures into the hanging wall and the footwall due to displacement in the fault plane. It has been widely observed in the field that the greater fault throw that you have, the thicker the damage zone will be. Getting into the survey details here, we're going to be working off the coast of Matagorda Island, which is basically the Texas shelf area of the Gulf of Mexico. It is a mega merged legacy dataset, and it is characterized by an extreme amount of acquisition footprint, and it also had some issues with processing and low signal to noise ratio. For our specific area of interest, we are going to be studying a small interval over the fault Bravos, which I myself name for simplistic reasons, and it is adjacent to the Clemente Thomas fault, which is a large regional listric fault in the area. The reason why we are choosing such a small interval of the fault to study is because that area is relatively unaffected by acquisition footprint. Now we will calculate our coherence volume. To the left, you can see a time slice that highlights the Clemente Thomas fault as well as fault Bravos, along with the acquisition footprint. Notice here that we are at 2088 milliseconds, and we can still see quite a bit of footprint even at this depth. On the right side, you can see an inline of coherence highlighting again fault Bravos. Now we will run our structure-oriented filter. So just going over quickly what structure-oriented filtering is that what you're seeing on the left there is a picture highlighting Kuwahara window filter. So the green dots are each seismic traces that have a pre-computed coherence within them. Those dotted blue circles are overlapping analysis windows that are basically looking for the seismic trace with the highest coherence and choosing that trace for filtering. What this does is this preserves faults and is able to reduce the mixing of stratigraphic reflectors as well as define those fault edges much more clearly, as you can see in the picture to the bottom. So now I will be getting into my main SOF parameters. So in the picture on the right, that is basically showing us what the filter is doing based on the highest coherent trace within each analysis window. So between 1 and 0.9 coherence, that is interpreted as protolith, and then traces that fall between 0.9 and 0.66 or 0.55, that is roughly the separation between the damage zone and the fault core. I will get into later why I chose these as my specific parameters for this filter. And this is what the filter sort of looks like on a geological outcrop. This is just going to try to sort of solidify the idea of how we are trying to use our filtering parameters to interpret what is actually happening geologically. And now here, I'm going to get into a little bit as to how I chose my main parameter. So this is 0.9 threshold that again is separating protolith from damage zone. I chose 0.9 here, and the reason why I chose this number is that with this parameter, you want to do two things. You want to suppress acquisition footprint and enhance geological features. The reason why we want to suppress the acquisition footprint is that we don't want our structure-oriented filter to be mistaking footprint for structure. That would kind of defeat the purpose of our whole study. So how we do that is you sort of just play around with your rainbow color bars in AASPI. So right here, this is just our default. Here I have it going from 0.5 all the way up to 1.0 coherence, just so I can kind of get a better color range for my actual data range within the data set. And this is basically cutting off the data maximum at 0.8. So right here, you can see that we have suppressed the acquisition footprint, but we have gotten rid of some of the edges around our faults, which we don't want to do. We want the filter to pick up on those outermost edges of those highly fractured zones that is basically the interpreted damage zone in this study. So for me, that kind of a happy medium where I was preserving my fault edges and suppressing the acquisition footprint was around here at 0.9 coherence. And then because we actually want to know what the noise is being produced by these faults, we're actually going to set our 0.66 and our 0.5 to 0 because we do want to filter over these faults because we are trying to say that these faults are naturally generating geologic noise, geology related noise. So here is a picture of my computed volumes. To the left is obviously our seismic amplitude data, and then to the right is our coherence, and then also the rejected noise that was removed as a result of the structure-oriented filter. As you can see, our anomalies are almost perfectly aligned with where the coherence anomalies are. And another thing that I liked about the rejected noise is that it is actually able to highlight acquisition footprint at a much better scale than you could with the coherence, which is why in this case, using the rejected noise as opposed to the coherence is almost going to be a little bit more useful for you in some cases. Now we are going to hone in on our area of interest in that Bravos fault that we imaged towards the beginning of this presentation. Here I've drawn an arbitrary section from that blue dotted line because again, we want to interpret these faults in these damage zones fault perpendicular as opposed to at an oblique angle. This is my sampling lines that I ran across the interval of my chosen fault. This is my more honed in area of interest. These sampling lines are just singular straight horizon lines drawn up in Petrel, and what they are doing is they are outputting the coherence and the rejected noise amplitude values approximately every 77 feet based on the bin size of this survey. Each sampling line is a little over 1,700 feet and spaced approximately 10 milliseconds apart. And this is what we're going to be using to estimate our actual damage zone and overall fault zone thicknesses. Here is what my sampling line data looks like. So we're going to be looking at sampling line 1, which is plotted in the bottom right. This is returning the coherence in blue and the absolute value of the rejected noise amplitudes in red. So as you can see, the peaks are almost they are perfectly aligned with each other. The same thing holds true in lines 2, 3, and 4, though the rejected noise amplitudes increase towards their maximum at a quicker pace than the coherence, which suggests a potentially wider interpreted damage zone than the coherence shows. Sampling line 5 was a little bit different. We actually saw a downtake in the noise right over where the center of that fault would be, where our coherence maximum for this line is. So I did a little bit of digging to try to explain this, and what I found was that this sampling line actually ran tangential to the Z crossing. And as I kind of looked around the entirety of the seismic volume, I found that the greater the curvature, the Z crossing, the more likely you would basically find these dead spots in the rejected noise amplitudes. So I would still cross-check coherence and the actual seismic amplitude data along with the rejected noise, just so that you're not interpreting these downtakes in rejected noise as leaving the fault zone, because obviously, as you can see from the coherence, we are right over the center of that fault and not outside of the faulted area by any means. Now here is the summary of the data. So in the top right, again, that is how I'm interpreting these damage zone thicknesses. Since we always see an increase in the rejected noise and the coherence at and above that 0.9 coherence threshold that defines the boundary between damage zone and protolith, we define both the rejected noise and coherence damage zone thicknesses to be their widths at and above coherence equals 0.9. And based off of that interpretation, the rejected noise amplitudes in that bar graph in red in the top left modeled thicker damage zones than the coherence did for every single line, which is again interesting to take into consideration that possibly the noise is picking up on these smaller fractures better than the coherence is. So going over some uncertainties, given our bin size, we're only able to resolve data points 77 feet from each other, and we're working with a small scale fault. So there is going to be quite a bit of uncertainty with this data. All sampling lines aren't going to be truly perpendicular to the fault core at each point, because obviously geology is not going to occur in perfectly straight lines. And since there is some presence of that acquisition footprint, that also could have slightly altered our noise, our rejected noise data. And then again, we are also working with a legacy merged data set. So there is also quite a bit of uncertainty that comes with using that old data. So some of the conclusions is that the rejected noise generated during structure-oriented filtering is very comparable to the coherence attribute and could almost be used by itself to assist with fault picking. Like you could almost load this into some kind of a CNN code up and use the rejected noise amplitude volume as one of the attributes that it uses to pick your faults. The rejected noise was also able to visualize regions affected by acquisition footprint to a degree that coherence just couldn't. And since, again, the rejected noise modeled wider damage zones than coherence, it could point to the fact that it might be able to identify fractured networks more reliably than the coherence can. Also, it picked up on certain anomalies that the coherence didn't really pick up on, like that anomalous lobe to the right that I've circled and pointed out that is blank on the coherence. That is actually happening tangential, or not tangential, it's happening adjacent to a bright spot. And I did double check to make sure that my rejected noise amplitudes were not correlated with my seismic amplitudes. So there could also be the possibility that it could help as well with identifying water, gas, or oil saturated zones. So some of the future work we're going to be doing, this same workflow is currently being applied to the Bacalhau field in Santos Basin offshore Brazil. That is a beautiful, very high quality data set that is depth migrated. So we'll be able to compare fault throw on that data along with our damage zone interpretations. And the comparison of coherence and rejected noise um, with the seismic attributes, GLCM entropy, and aberrancy. The interesting thing with aberrancy is that aberrancy is an attribute that can pick up on anomalies that coherence can't, specifically faults with small offset. So if we can show that the rejected noise is also anomalous over aberrancy anomalies, then that's further proving up that the rejected noise is modeling or picking up on these smaller fractures better than coherence is. I would like to thank my amazing mentor, Dr. Heather Beadle, Dr. Kurt Marfert, Dr. David Lugo Robles, Dr. Brett Carpenter, and then Pamela Blanca Dufau. She was the master's student who came before me. She worked a lot on this data set and kind of got me started. And she was kind of the person who initially noticed this relationship between the faults and those rejected noise amplitudes. And obviously, I'd like to thank the rest of my team at AASPI and all of our AASPI sponsors. Thank you so much for allowing us to kind of go down these rabbit holes and continue our educations. Thank you.